So truth tables are a way of proving how a logic circuit will work. You need to be able to create one from either a circuit diagram or an algebraic expression like we've got below. Now, the first step I'd advise you to do is make sure you've got one column per variable in your equation. So we've got A, B, and C here, so I need A, B, and C columns. The next step will be to write every possible combination of A, B, and C. If you imagine they're all switches, we could have A, B, and C all being off, C being on, B and A being off, etc., etc. The way to make sure you don't miss any is imagine it's just 3 bits of data and you need every possible combination. So start counting 0, 1, 2, 3, 4, 5, 6, 7. And 7 plus 0 is the 8 combinations for a 3-bit number. Okay, so that's my tip for you there. Once you've done that, step 2 is then doing a column for all but one of the operators. So what we've got here is that's because I couldn't draw the line. So if you ever see me writing a little apostrophe, that's just saying not A. So we've got a not A column. So not A is just the inverse of A. So if A was 0, not A is 1, and vice versa. Then we've got B and C. So B and C can only be 1, this column for that operator, if both of these are 1. So you can see there, both of those are 1, so it's a 1. There, both of them are 1, so it's a 1. Okay, once you've done that, we're nearly done. Because then we've just got this operator left. But this operator is essentially this whole equation. Because we've got a not A column on one side and a B and C column there. So we just need to perform an OR on those two. Those two are the inputs to our OR gate. So our OR gate states if any of these are a 1, then the output must be a 1. So because A is a 1 in those 4, it's all a 1. Then there's 3 zeros and then a 1 because that's a 1 there. And then we've got our truth table for this equation here. For this equation here. We now also need to be able to potentially do the same thing for a logic circuit. So logic circuit, some people find these harder, some people find them easier. Essentially, you're looking at the same things. You want effectively a column for each gate. The final gate, final logic gate might as well be your answer column, but you want one for each of these gates, and you want your ABC. So I want to do all my possibilities for A, B, and C as step 1. Then I want to fill it out per gate. So if we think, I've got here A and B. So A and B, if A and B are 1, which are these two down here, they'll be a 1s, otherwise they'll be all 0s. That's not C, so that's an inverse of C. Okay, and then it's also done this one. So this one is A and B or not C. So A and B's there, not C's there, so it's just an OR. So if either of these are a 1, that's a 1. Yeah. Okay, so that's all correct. Once I've got that, if we think what's our final gate? Well, our final gate's a NOT gate. So we've just done that one. So our NOT gate just inverses that one. So our Y is just an inverse of that column there. And it's done. So now we've done a truth table on a logic circuit and a Boolean expression.